तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will start to discuss the concepts of illumination and shading in computer graphics. This is one of the most important stages in computer graphics, which can be visualized as almost the last most important and vital stage in a 3D graphics pipeline. Well, of course, you may have a two-dimensional transformation at the end to a viewport on the screen. If you remember the stages of the graphics viewing pipeline which we discussed earlier, and of course, very lately we have seen different methods of visible surface detection, which is followed by illumination shading. In fact, if you remember, most of the algorithms, in fact all of the algorithms on VSD or visual surface detection talks about a pixel or a polygon being rendered. Okay? And when we were discussing that fact, we did mention that we will discuss the algorithms and methodologies and concepts of illumination and shading of a polygon or a point later on. So, this is the time now which we need to discuss about illumination and shading. So, that is the key idea of the lecture today and in the couple of lectures following. And you remember this diagram, you definitely remember this diagram, which was used for two different VSD algorithms. One was used for ray tracing or even the Z buffer, where a particular pixel xy is rendered based on the intensity obtained on the polygon which is in front. So, if you are talking of shading a polygon, it is it can be visualized as a 2D polygon fill algorithm with intensities obtained from the 3D data. And prior to that, of course, we have the Z buffer or a method based on ray tracing, where of course we take a pixel out from a point x y on the image plane, or we can process polygon wise or object wise, where we process polygon and one polygon with the other and do the Z ordering or depth ordering to find out which is the nearest polygon, in part or in whole at a certain point or a certain pixel x comma y. Okay. So, once that is done with the help of ray tracing or Z buffer, as you can see that this ray can be visualized either as a ray traced backward to the direction of the light source, or also could be visualized as at light rays coming out from the 3D scene and impinging on the projection plane. Well, if you are interested on a particular point xy on the screen, this point will be illuminated due to the shading effect of the nearest polygon at that point, which is this one, let us say. Okay. So, that is what we have to see. And if you remember raycasting, because that was the recent one which we talked about very recently in the last lecture, that is easy to visualize with respect to this diagram. The intensity at that particular point xy on the image plane can be visualized as the intensity obtained due to that point on the polygon in 3D. So, now when you retrace the path of the light ray and back and strike the polygon, you have to basically illuminate that pixel based on the intensity reflected by the polygon at that particular point. And the question now comes is, how much of a light ray will be reflected by a polygon or a point on the polygon or on an object? That is the key. We have to model that process and find out how much amount of light is deflected from an object point towards the viewer or the projection plane. Well, it depends on various factors. Just to name a few factors, it depends on the light source. It could depend on the number of light sources if you have more than one light source. So, there could be various types of light sources and at various positions in the scene which are radiating light. Of course, typically if you say that we are visualizing an outdoor scene, then of course we have only one light source, which is the sun. But typically if you take a classroom or an indoor environment, you may have multiple light sources, okay, radiating light equally maybe or unequally in different directions. So, that is the first thing which you have to model. Second thing, we must find out that how much fraction of the light source emitted by the light source or the light sources, one or two light sources may be there in the scene, and a fraction, a very small percentage of that light falls on a particular object, and that too in a small planar patch represented by a polygon, and that too one particular pixel. So, a particular pixel will also receive some amount of light, and depending upon the surface properties, the most important surface property being, let us say, the surface reflectance properties, which dictate how much amount of light will be reflected from that surface. That will dictate, that will actually determine the amount of light which will be reflected away from the surface. That means, there is some amount of light which is falling on a surface and something is reflected back, something could be absorbed, something to be reflected back along a particular channel, okay, like a single ray, or it could be diverse and equally dissipated in all directions. Several things may happen depending upon the surface properties. So, that is what is going to happen, and that is what we have to model. But there are other problems which come here. Number one is, we have to model, we have already seen that we have to model a light source or multiple light sources. Number one, we have to model different parts of the object which may have different colors and different reflectance properties. We talked of reflectance property just now, and we will see mathematical equations which are used to model such reflectance properties. That is okay. Now, it could be possible that the light could be of a particular color, and the surface object itself could be some other color. Okay. So, let us say we are working in a white or yellow light environment, and we are working and we are viewing an object which could be red or blue in color. Okay. So, depending upon the surface color and the surface reflectance properties, and depending upon the illumination color or the intensity, we may visualize different type of shades of colors and intensities of a particular scene. Okay. So, these are the various facts, first of all, we have to model. And what are you trying to do this? When you are trying to create a scene, either in a, it's a question of virtual reality environment, or to give visual realism, which we talked about in ray tracing or VSD algorithms. If you look at reality for that matter, in a classroom type of a scenario or an indoor environment, you may have one or multiple light sources. It is quite difficult for you to visualize at what based on what viewing angle and what direction and what point, how much amount of the light you are seeing. Why? Because a scene may have various objects. Each of these objects will have different type of parts, different colors, different reflectance properties, and there could be multiple light sources. There could be a scenario where the amount of light source impinging on an object, some part of the light ray, suppose the light source is here and some amount of light falls here on the object, and some section of that will be reflected along a certain direction. You may have another object at that point which will again reflect the light and so on. So, there could be multiple reflections which are possible. I am not saying the multiple reflections in the case where you have only multiple mirrors. The objects themselves produce inter-reflections, correct. It is possible that a light ray may fall on object number 1, go to object number 2, go to object number 3, and come back to object number 1. So, this is the reality, and there are in fact, truly speaking, in reality, uncountable number of rays, infinite amount of rays which are traveling around the universe and also in space and also in the classroom, even with a single light source. And what happens then, of course, you should ask a question is when you are viewing it with your own eye, how can you view it? Yes, you can. When you also use a digital camera, you view what, but what do you view? You, at a particular given point of time, and when you are looking along a particular direction with your eye, which is the natural sensor, or the digital camera, which is an artificial sensor, among all the different rays, virtually you can imagine almost infinite amount of rays, okay, infinite rays reflected in all directions with different lighting and proportions and different intensities. You can visualize that using a digital camera in a small region, in a small aperture, you are capturing only a small section of those light rays, but that is what we have to model as well. with our eye also, you can rotate yourself in a classroom right now, and what you will be seeing is you are reorienting an aperture through which the light rays are falling on your retina for the human eye. Okay. So, among all the different rays which are traveling in front of you, you are only seeing a section of those rays which are passing through your eye lens, through the aperture and falling on the retina, which are sensitive to certain light intensities. Similarly, in a digital camcorder or a digital camera for that matter, you have the sensitive charge coupled devices which will transform the light to electrical energy, but at any given point of time you cannot capture all the rays. For a particular snapshot or a screen, okay, you are only capturing a small section of those rays. And what are those rays constituting of? Some of those rays could be even such that could be directly coming from the source, one or two more, but you are viewing an object, most of them are getting reflected by the object and coming towards you, from that to from different objects. Of course, at any particular given pixel point of pixel xy, you will of course be seeing only one particular point of an object, that is true. And of course, the amount of the light which is again reflected depends upon the surface reflectance properties. A perfect dark object will have zero reflectance, okay, and you can have something like a snow or a silver which will reflect almost all of the light which it receives. So, there are various degrees of reflectivity of surfaces which you have, starting from absolute dark to absolute bright and grey colors and different shades and intensities and colors in between. Okay. And those are the different rays which are, first of all, could be directly reflected onto the projection plane or view plane in this case for computer graphics. It could be the case that these objects which you are viewing, in addition to direct rays of the sun or the light source which it is receiving, it also receives interreflected light rays. It also receives interreflected light rays from the object transmitted to this. So, that is what you see here, that this particular light ray which is reflected from this object point of the polygon to the projection plane could be resulting due to rays of light which could fall directly from the source to the projection plane at this point, or rays indirectly coming from or reflected from different objects, one or two more objects, and then falling all of that again on this point and then get reflected back. And this concept happens at each particular pixel on the projection plane as well as on the each object point which is reflecting the ray. So, you have all sorts of rays coming from all different directions impinging on the object or object points, and the object points also radiate, okay, or reflect back these light rays, maybe in all directions, maybe towards a particular direction, depending upon various properties of the surface on the object, which are termed as reflectance properties or color of the surface. Okay. Now, well, you see, if you want to model this entire thing in a typical scenario in a classroom, if you see, and I did say some time back, uncountable number of rays, infinite rays exist in a 3D space, even in an indoor environment, and there is no way you can model this accurately enough to give the impression that it is a true picture. But still, the computer scientists and other engineers working in the field of visual realism, virtual reality, computer graphics cannot stop. We have to create pictures for various applications which we have seen from the beginning of this series. Okay. So, we will make certain assumptions and see how to model this process of illumination and shading, because so far we have I have tried to give you an idea about how difficult this problem is, or in computer science terms what is called as the shading is a very hard problem. So, that is the point which we start now, that the process of illumination and shading is a hard problem, and I hope in the last few minutes I have tried to give you an illustration of or describe why shading is a very hard problem. So, we need to create a virtual reality, say a classroom, as I was talking about some time back, of a real scene which involves, there are various methods by which the shading and illumination is done for complex 3D scenes. We need to model and position several complex objects in the 3D scene, that we have seen as the first stage of the 3D graphics pipeline. Okay. But once that is done, you determine using the visible surface detection algorithms, find the visible surface at any particular point. You can use Z buffer, the Z buffer algorithm, or ray tracing. I think we will stick to mainly these two algorithms because they are very common, popular, and they are the most sophisticated. ones which are used. Okay. Among those suggested in the classic literature of the books which you have been following, those are the two which are most commonly used. Okay. And I am not saying they are always simple to implement, but they are quite algorithmic, and one of them, the ray tracing, in fact simulates the real world, which is the essence of virtual reality. So, using VSG algorithms, determine this visible surface and project the view with respect to the viewer. Okay. Project the view as you are seeing it, and obtain the shading using surface normals, obtain the shading using surface normal, surface properties and light sources. That is what you do next. That is what is the main essence of our talk today. This is the most important part, where we talk about shading using surface normals, surface properties and light sources. Then obtain shadows from occlusion. That this is an important part which we discussed at the end of the discussion on ray tracing, that ray tracing is probably the most efficient method by which we can implement shadows. Okay, because shadows gives you, we had seen in a lot of illustrations at the beginning of the lectures in introduction, when I gave lots of examples, that shadows really give. When you probably do not see shadows, you can almost immediately guess this is a very crude approximation, or a very approximated scene which is generated, because typically except planets, asteroids and satellites in space, nothing hangs in space. Okay. So, we have objects sitting on a surface. Okay, you are sitting in a chair, my hand rests on a table and so on. So, if we have one or multiple sources, you are bound to have shadows on the platform in which the objects are resting. Okay, we will see examples of that later on, but you have already seen examples earlier. So, you have to implement shadows. So, that is another key part, and ray tracing could help in this particular case. So, in a real world environment, light rays flow in almost infinite directions. I talked about this some time back, and some of these light sources are directly from the source and some are reflected from shiny surfaces of the object. Of course, the surface reflectance properties have a very important role to play here. If we have an almost perfect dark or a black object, it will not reflect any light. Of course, even if it reflects a small amount, that can be considered negligible. Of course, when you talk of shiny surfaces like aluminum foil or silver, or it can be gold, that reflects almost the entire part of the light, which a special case of that also is a mirror surface. But there are lots of other shiny surfaces. Okay, you can produce a shiny surface using a glossy paint. Okay. So, some parts of the surface may reflect more, some reflect less. It all depends upon the surface reflectance properties, to what extent it will reflect, and of course, in what direction. But I talked about this, that in a real world environment there are virtually rays going in almost infinite directions, and we have to capture only a small subset of that. And that is almost impossible. In fact, why almost impossible to model. So, we will see what the simplistic assumptions are to generate a scene which appears as close as possible to real world. That is the essence, and that is the motivation behind which the computer scientists and computer graphics engineers have been working to try to come up with sophisticated algorithms, maybe a little bit complicated, not too complex if possible, to generate realistic scenes in virtual reality, which may appear as close as possible to reality. It may not appear absolutely real, true, because almost everybody given to photographs, however realistically one generates by a graphic scene, and a photograph taken from a digital camera, even a layman could distinguish between the two. But our objective here is not to make scenes which appear too virtual. Let us say I am talking of cartoon pictures, okay, or even some video games, the old traditional ones. Okay. Some of the video games have a lot of effects of 3D shadows and good amount of animation and all that, but I am talking of reality in terms of education, training, scientific and engineering studies, where you need to provide a realistic scene, whatever you are modeling, and give it a visualization such that it appears almost natural and real as possible. Again, I use the word almost and near, because as I said that we cannot model infinite rays, and a fraction of an infinite rays passing through a small aperture, you can visualize that is also an infinite in some sense. So, that also cannot be modeled. So, what we model is a set of finite amount of rays coming out maybe from the source, some of them reflected by object, inter-reflected by other object. That is the most difficult problem to simulate or model. Inter-reflections, which causes a particular type of illumination, which we will see later on. Okay. But right now we will see that we will consider certain simplistic models and try to create scenes which are almost as real as possible, and that is what we are studying computer graphics for. So, coming back to this problem, which says why it is a hard problem, the problem of illumination and shading, as to why it is hard, because in a real world environment light rays flow in almost infinite directions, some direct from the source and some reflected from shiny surfaces of objects. A real world image taken using a digital camera will only capture a small subset of these light rays or light energy passing through the small area. Okay, so, I repeat again, a real world image, that is not what we are simulating using computer graphics, but the image captured and a snapshot taken using a digital camera will only capture a small subset of this light energy, which is again infinite in terms of the number of rays passing through this small area. And so, we have to make a crude approximation of that area. That approximation will be quite close to reality, it will not be far away. It will, and we have to ensure that how close we can go to reality to find out to ensure that scenes look as real as possible. So, to accurately construct a picture of this room, say the room in which you are sitting or studying, or the room in which the this current computer graphics lecture is being recorded, and use that to model and reconstruct a picture of this room via computer graphics, we have to simulate this illumination process and be able to calculate the shading at each point of each surface in our scene. So, you see the difficulty now. If you look at this room in which you are sitting, or this room which I am currently delivering this lecture, well, there are lots of light sources here which are emanating light in all directions, of course, most of them coming towards the object. And when you talk of objects here, the tables and the chairs in which we are sitting here, or the objects, the system, computer system which we are working, or the body parts, the cloths, fabrics which we are wearing, each will of them will be receiving light in virtually infinite directions. They will be reflecting light also in different directions. The interreflection rays will also come, they will be also reflected back, and so on, and that is where you have to model this as accurately as possible. How is it possible to model infinite amount of rays? Because you know that there is no way a value which is infinity or a database cannot hold infinite amount of records. We can't do that. We cannot store infinite amount of rays, information about that in a system, but we can store as much as possible. We will try to see whether that is the way by which illumination is modeled, or some other approximations are considered and then combined with the VSD algorithms to create virtual reality, visual realism in virtual reality. That means you should be able to view reality through computer graphics. That is the key essence. And then we often have an approximated view, or often an approximated view is generated using many complex formulations and algorithms. So, that we will see that how this complex environment is modeled using some complex formulations. We may not have time to go through all sorts of complex formulations, but at least some of the basic concepts of illumination and shading we will discuss, algorithms based on those, and we will see how different concepts are combined together to provide real pictures. Of course, there has been a lot of developments on this illumination and shading. I talked of this term called radiosity, which we discussed at the end of ray tracing. That is probably one of the best methods so far, and advances based on those to create visual realism of pictures in virtual reality or computer graphics. Now, let us try to understand the process of illumination which involves the surface normal, source and viewer directions. And we will also see why these three vectors are the most important vectors in terms are important key parameters, I should say, in trying to obtain the illumination of a particular surface. In this case, what I have taken is a a upper part of a spherical surface, it could be also a cone, does not matter, and I am interested to find out say the illumination at this point O, you can consider it to be a small planar patch or a single pixel. Let us say you have shot a ray from a certain pixel xy from the projection plane towards this object, and that pixel ray has struck the curved surface or solid object, whatever the case may be, at that point xyz, which is labeled as O in this figure. We will go back to this figure. So, there is a small planar patch, a polygon there, we can assume a small polygon or a single point, and that point will have a surface normal n. You can easily compute the surface normal n for any curved surface at any point xyz, or even if you approximate it using a planar patch. We know how to do that using, we have seen about wireframe diagrams, sweep representations, how to approximate curved surfaces with the help of small polygonal, triangular or quadrilateral planar patches. Okay. So, that is what we are talking about, this point O, a small area around this, and we want to illuminate that area and see what is and calculate what is the intensity of that point when viewed from a certain direction. So, n is the surface normal of that. S is the light source. So, the light rays are coming from S towards the object O, and V represents the viewer direction. V represents the view direction. These are all with respect to this point O, which is on the surface. Okay, it is a curved surface. Now, what are these two angles? These are very important. I have marked two angles, phi and theta. Theta can be visualized as an angle between n and s vectors. I repeat, what is n? N is the surface normal, which is written here. S is the source direction. Of course, the direction of the arrow could be reversed to point towards the vector pointing toward the source direction, although this arrow marks the direction of the light source which are falling on the object surface from S, okay, but you can reverse the arrow direction and say that this is my S direction from O towards S. So, that is the source direction, and V of course is pointing towards the viewer direction. So, theta is the angle between the surface normal n and the source direction S. N and S are, I repeat again, surface normal and source, and theta is the angle between n and S. What is phi? It is the angle between the surface normal n and viewer direction. V is the viewer direction. We can have that viewer direction to be arbitrary, source also could be arbitrary, n of course depends upon the properties of the surface object structure. Okay. Now, if you must visualize this figure in 3D, this is a very careful observation, although it is not mentioned in this slide, that this figure is in 3D. What this basically means is S, N and V may not lie on a plane. This is a very interesting fact. Remember, if you take any two vectors, you can form a plane in, consisting of those two vectors. There is absolutely no problem. Any two vectors in 3D space, you can actually find out the plane. You can find out the plane on which these two vectors are lying. That is absolutely not a problem. Now, what about the third vector? It may or may not lie in a plane. In fact, you should now visualize that this V does not lie in the plane in general. Of course, it could be a special case when all of these V, N and S, there are three vectors, look back into the screen, N, S and V, the three vectors could lie on the surface on a plane which is the screen. If you assume the screen which you are viewing as a plane in 3D, a surface in 3D, then all of these could be lying on a plane. So, that is a special case, but what you should visualize is if you have S, if you have N, the V may not lie in the same plane of N and S, it could be anywhere. Okay. If you have N here, the S there, okay, and the V like this, the V could be anywhere in 3D. Okay. That means you want to view that object surface or that object point from any direction, and you should be able to calculate the intensity, because when you keep changing V, not only in that plane of N and S, but anywhere in 3D, actually V could align itself with N, V could align with S, it could be anywhere between N and S or anywhere, only the restrictions are that those angles phi and theta should be less than, in absolute terms, pi by 2 or 90 degrees. Okay. If you have a look at that, that is the only restriction. The angle, in fact, theta is sometimes called the angle of incidence, because this is the incident ray coming from S, and with respect to the N, we have an angle of incidence I, but I used a value theta here. You can have the angle of viewing angle phi. So, theta and phi are the angles used here, but this figure is in 3D. V could be anywhere. Of course, N and S could be anywhere. N of course anywhere means it is dictated by the object point at that particular point. S of course depending on the light source, and V could be any viewer point. That means you should be able to view this object point from any point in the 3D scene. Of course, with the restriction, again I repeat that phi and theta, phi should be less than 90 degrees, plus and minus, that is number 1, and theta also should be less, otherwise there will not be any light source falling on that object point to illuminate it. Okay. So, these are the two important facts of V, N and S. V could be anywhere. This should be visualized as a figure in 3D. Okay. Although the figure shows that it's a two-dimensional figure, but I keep repeating this is not. Only restriction comes with this will come in the calculations when we talk of equations and models. We will see that these angles phi and theta in absolute terms should be less than pi by 2 radians or 90 degrees. Okay. So, now coming back to this figure, this is the scenario where you are talking of just one light source coming from S, hitting this object point at the point O, and these light rays could be going in any direction, but you are observing it from or the viewer or the projection plane is located in such a direction that it is pointed to by this vector V. Now, what are the different scenarios which can happen in terms of light rays coming and light getting reflected? Let us see one of this scenario here. Yeah, this is a scenario where the viewer direction could be anywhere. I was talking about this some time back. These are the 3 other possible viewer directions, and again you should visualize this picture in 3D. V is a 3-dimensional figure, as is N and S. V may not lie in the plane constituted by these two vectors N and S. N and S, two vectors form a plane. That is absolutely you can find that out, what is the equation of that plane. We have done that exercise already in 3D structured 3D solid modeling and VSD, visible surface detection algorithms. Okay. But the V, when it lies on the place of N and S, is a special case only. Okay. It can lie anywhere in 3D, and the phi will be just the angle between N and V in 3D. Remember, if this is N, this is your V, we can position it anywhere, okay, and the angle is the angle phi which we are talking about. So, there could be different values of phi. I leave it an exercise for you to take each of these directions as your view direction and draw the angle phi. So, the view direction could be anywhere, number 1. Number 2, an important fact is that the light source may not only come from one direction, but it may come from many directions. What do you mean by light source coming from different directions? We talked about this. This was the key factor which led us to understand that the illumination and shading is a hard problem. If we see that picture again carefully, the main vector S, which is shown in the reverse direction, shows the light ray coming from a light source S, but there are other dashed arrows which also show that light rays could come from all other directions. Those light rays could be due to various reasons. First reason, there could be more than one light source S. There could be S1, S2, S3 and so on. Of course, if there are too many light sources, there will be too much of illumination, all that. One of those may not have a significant role to play because there are other ends light sources. But when you talk of one light source and a second and a third, yes, there is difference in illumination as you are viewing a particular object. That is always true. Okay. That is a very significant information, because when you switch off a light source and you switch on one, then the amount of light which falls on an object and gets reflected will definitely vary. You can do that experiment right now. If I request one of you to come up and switch off one of the light sources, can you switch off one of the light sources? As you can see now, one part of my face is dark and one part of my face is bright. I would request the light to be switched on. You can see that you have uniform illumination because both light sources, there are two light sources basically illuminating my face. Yes, keeping this on, can this be switched off? As you can see. Now, this is a fantastic effect. As you can see, only my right side, which is to your left, is my portion of the face which is getting illuminated, and that is because one light source is on, and this is a back face with respect to the light source. So, this has to be switched on for this part to be illuminated. Can you switch this on? Now, there are two light sources. Now, of course, you can have effect of more than 2 or 3 such light sources illuminating an environment, okay? But of course, it does not matter much if you have more than quite a few. So, but 1 to 2 to 3 light sources, yes, there is a variation. So, those arrow directions could be indicating the directions of the light sources or the direction of the light rays coming out from the light sources and impinging on the object. Okay, I hope this was a very good, nice live demonstration which you had recorded, which you had just seen now in terms of the light sources affecting the illumination of parts of objects in a 3-dimensional scene. Okay. Number 1 point, light sources is number 1. The number 2 fact, which is also true, is those directions which you saw in addition to the main light source S could be interreflections, that means there could be many other objects present in the 3D scene, and most of them assumed to be non-dull or non-dark objects, because if most of them are dark they will not reflect light. So, there should be shiny or shiny type of object surfaces which should reflect light, and those reflected lights of the objects, other objects, may not actually reach the viewer. They could get reflected from some other direction towards me or towards the object which you are viewing, and then get reflected back to your projection plane or the camera which is recording the scene. And the more the number of objects you have the 3D scene, more amount of interreflections. In fact, you can visualize just 2 objects in a 3D scene in a classroom which is surrounded by the floor, ceiling and the walls, will have lot of scope of interreflections, because there could be a principal light source falling on object 1, getting reflected to object 2, going to a ceiling or a wall, coming back. In fact, I cannot show a further situation. You can right now yourself as students look up into the ceiling or look down on the floor. You can see that most parts of those objects may not have the illumination directly obtained from the source, light rays coming from the source directly. I repeat, parts of the ceiling, floor and wall may not have light rays coming from the source directly, but still they are illuminated. Maybe that illumination strength or level is small compared to the illumination of other objects which receive the light rays directly. But where does those light rays come from? From those other objects which are not receiving light rays directly. Let us say, even if you are working, a very simple example is, if you are walking in the evening in a full moon lit night, okay, in a full moon night, what will happen is there is no sun, and the light rays which you are seeing in the environment, however small the illumination may be, are due to the light rays of the moon. Now, moon does not generate light rays like the sun. Where does it get? Moon surface receives, the surface of the moon receives light rays from the sun directly, reflects it back to the earth surface in some proportion. A small percentage reaches the earth, okay, other fraction goes elsewhere as well, and some of those light rays which fall on the earth surface, when you are viewing those object surfaces, it could be any 3-dimensional scene, outdoor, in the evening, in dark, is not fully dark. You can see some objects in a full moon day, because those light rays, however small intensity it may be, illuminates those objects. Those are indirect rays reflected from the moon surface to the earth surface and then going to your eye. So, if you use a camera, the similar thing may happen, that you have indirect light rays interreflected from various objects, finally hitting the floor, ceiling or the walls of a room, and then getting into your eye or getting into the projection plane of the viewing system or the camera which is capturing those light rays. So, now you can visualize the hardness of the problem in terms of trying to model so many scenarios in terms of light sources, surface reflectance properties of objects, and more than that, the hardness comes from this interreflection. It is impossible to model that. You can make a large supercomputer run from Y days or months for years together to model that object, and still you may not get the actual reality. You will of course get close to visual realism. In terms of visual realism, you will get very close to reality, all right, but it will not never be real. Okay, because I think a very simple statement if I make, the computer cannot hold a value infinity, or in a database in a computer I cannot store infinite values or records, is a sufficient clue to tell you why I cannot model infinite rays which are moving in this universe, space, or even this classroom right now. So, 2-3 light sources and some approximations based on the fraction of the light which is reflected directly from the object source towards the viewer or projection plane can be substantially modeled with great degree of accuracy. The most difficult part is the interreflection. So, if you look back, as I was talking, we left this diagram long back, these light rays may be other light sources, due to other light sources, but most of these are the result of interreflections or indirect rays reflected by other objects in 3D scene in the environment and impinging on this surface. Okay. Now, where do these other objects which are reflecting light get the light source? Yes, they are getting the light source or the light rays from the same source which we are also getting, or the main object is receiving light. One or two light sources may exist and they are illuminating the whole three-dimensional scene. So, all objects, or at least the frontal faces with respect to the light source, are receiving light. But when interreflections happen, there are indirect rays which are reflected, direct source falls on the object, get reflected out. Now, some of these, if they do not reach the camera or the projection plane or the human eye, they will reach some other object and then get reflected again, and so on and so forth. So, it keeps going on. As it keeps traveling, the light source intensity reduces. We will see that sort of a model which is also used in general. And then what happens is, if interreflected rays creates a scenario, I will use a term right now and come back to that term later on, is what is called as ambience or ambient illumination. It is a simple term to talk about, and that is what is used to model the most hardest part of the problem. Just almost a single one or two terms are used, one or two variables are used to model the complex part, and that is the most coarsest part of the simplification in terms of responsible, that is responsible for generating the coarseness of the picture, and that is what does not give the picture, making it as real as possible to a real picture. So, these are interreflected rays reflected directly from other objects. Those objects could be receiving the direct light sources, the rays from the source directly and getting reflected here. So, you have to model the figure here in terms of the number of light rays. Ambient illumination is often used, and then this object, we do not know how much of this light will reflect towards the viewer, how much fraction it will reflect in other direction. That depends on this light intensity, the light color, the surface reflectance properties, surface color. So, there are 3-4 facts which are responsible for that illumination of that particular point, and of course, your viewer direction, that is the angle phi between V and N, will of course be the key, will also be one of the, not the key, the one of the responsible factors. We will see that the other angle, the incident angle which I talked about between the surface normal N and S, is actually the main key factor which is responsible for the illumination. If you look at this equation, which is can be considered as the basic equation of the illumination model, which we have been talking so far, it takes into account two different conditions. It says I of V of x y. Now, that must be understood, but before that we will say that that is intensity at a certain point x y on the image plane is a function of all the two angles phi and theta, which we have described earlier. Rho is the reflection coefficient, we will come to this term also later on, reflection coefficient at that point O on the object surface, and SL is the intensity of the light source, plus of course this term, which is very important and interesting, which I just talked now, that it is the ambient illumination as a function of V, which takes care of all these interreflected rays and ambient terms. So, the intensity at a point x y is a function of one of the light source. If there is only one, of course, if there are two light sources, we will see later on that there could be two such functional forms, f1 plus f2 with similar behavior, two angles phi and theta, reflection coefficient rho, light source in intensity SL, and ambient terms. So, these are the, so you can see there that we are talking of two components now of the light source, two components of the illumination model, or two components which result in the illumination at a particular point x y. One is the ambient term, which very much simplifies the entire hardness of the problem which we have been talking about. It is difficult to set that term, we will not discuss methods by which this term is typically set, but you can vary it in the low range somewhere, that A as a function of V. Now, that could be assumed to be a constant, we will see generally that A is assumed to be a constant, invariant to B, it does not depend on B, but it may. If you have a surface which the ambient illumination appears different from different directions, then it becomes a function of V or the angle phi, whatever way you look at it. But that is the component which simplifies the interreflections. The main component of illumination comes from the source, direct rays obtained from the source which hit. So, phi, theta, rho and the light source intensity and color. So, those are the main factors which are responsible. Interrelated, of course, in some sense, we will see in some cases the phi may be important, the theta may not be important or vice versa, and we will see all these two put together as we go and look back into the equation again when we are studying the process of illumination which involves surface, normal source and viewer directions. This gives the right hand side summation of two terms gives the intensity at a viewer direction for a particular value of x comma y. Now, what is this x y related to 3D? We assume here, imagine ray tracing, a particular point x y on the image plane, particular point or pixel x y on the image plane, shoot a ray out. That ray will go and strike a particular object which is in the front at a certain point x y z. So, we say that the intensity in that viewer direction x comma y based on the direction in which the light rays are being shot back will depend on the object point O which this ray has gone and struck back. This viewer direction V which is shown in the figure is the inverse direction of the light ray which is traced back or casted back from the image plane towards the object. So, we are assuming here that a ray casted out from x comma y is travelling in the reverse direction of V and goes and hits the object O first. Object O. There could be other objects. Of course, if it hits another object, that is the point which we are seeing at a particular point for a particular pixel x comma y. But if that is the object we are considering, that is the one which we are interested in. So, that is why that I as a function of V x y basically means that I have the image plane in a viewer direction V, okay, and there are parallel rays which are coming out from each point x y in the image plane. All of these are parallel rays coming out in the viewer direction of the with respect to the viewer direction. I am talking about the viewer direction with respect to the object point O. So, whatever V I am pointing to, the light rays are cast in the opposite direction, because actually the light rays would have gone and hit the eye or the sensor at that particular point if you had put an eye or a digital camera. But in terms of computer graphics or virtual reality, we are casting rays back from all points x I, y I. So, take one of those rays, cast it back in the direction opposite to V, comes and hits the object surface O. So, that is why V x y depends on this x y z point O, its reflectance properties, east normal and the theta and phi, all those angles plus the ambient term, these all, at least these could be modeled plus a few more. This is just the starting point of the illumination model which we are recommending right now, and we will see a lot of formulations on top of these in terms of the ambient term and when does it depend on theta, when does it depend on phi, when does it depend on both, to what degree, more does it depend on theta, more does it depend on phi, that means the angle between the V and the N or N and S, we will see that later on, and how much does it depend, it does depend on rho, the reflectance properties, which could be very dark, 0 I repeat, rho could be varying from a normalized value 0 to 1, 0 for a perfect dark object, black body which does not radiate any light, to a very almost shiny surface like a snow, silver, aluminum foil which I was talking about, where rho is 0.99 or close to 1. Okay. That is what we are talking about. These are the parameters which affect the illumination at a particular point x y in the corresponding viewing direction. So, I repeat again, that is the explanation of this V x y which we are talking about, that in the viewer direction we have the projection plane, and at certain point x y this V will go and struck the image plane at a certain point x y, or from the point x y you would cast the ray reverse direction to V and let it struck the object point or object surface at point O. Okay. So, I hope the explanation of the terms and parameters of this equation are clear by now as we start analyzing in details each term one after another. But before we do that, we talk of typical compromises and simplifications which are used to model realistic scenes. The first of the assumption is the uniform media. Well, when you are seeing me and I am looking at you, there is probably only air in between. From the earth surface, when we look towards the sun, most of the space is a vacuum. Okay. So, and where we are probably looking into a swimming pool which is very crystal clear, the media is water. We assume that the media is not turbulent, Even if air is turbulent, it does not matter much, of course, but there could be mediums like glass, water, through which rays could also flow, non-opaque objects, translucent objects were part of the rays flow. We are assuming whatever be the medium, pure clean glass, water, air, vacuum, it is uniform. That means the rays do not get disturbed. The concept of ray casting, where light rays travel along a linear path in one particular direction without deviation. Of course, if it goes from one medium to another, it may be deviated. We know those concepts from basic laws of physics, all right, but we assume that there is just one single uniform media between the object and the projection plane, that is all. There could be many objects in the 3D scene, some of them could be objects, some of them could be transparent, some of them could be translucent, that is all right. But with respect to the objects in a 3D scene and the projection plane, which is viewing a set of objects here, we are assuming that the media is uniform, and light rays coming out finally from an object surface will go undeviated in a linear path and hit the projection plane at a particular point x comma y. That is the first assumption. Next one, opaque objects. Typically that simplifies the scenario still further. Why? If you don't, well, if you have opaque objects, you don't need to worry about interreflections much. I am sorry, you don't have to worry about rays which are absorbed by the object, transmitted through in between, like a glass or a translucent object like a plastic, let us say, okay, with which you can see partly which you can see, okay, a transparent rubber, let us say, and the objects reflected back and reach other. The ambient terms become more and more invalid if non-opaque objects exist in the scene. The complexity is a little bit different, because now when you ray cast, you have to visualize not only rays which are received directly along with ambient and reflected back onto the sensor or the projection plane. I use these terms interchangeably, when sensor in a real world and a projection plane in computer graphics, you should try to put this together and see the difference. Okay, so I am putting that scenario in front of you, but in terms of non-opaque objects, when the object surface is non-opaque, there could be light rays passing through the object, coming out and then also moving towards the projection plane. And where are those rays coming from, passing through the object? They are the other rays reflected from other non-opaque or opaque objects, for that matter. They all combine together, pass through the object, come out of the surface. We have not seen a picture which does that. Okay, that can make things very complicated. Opaque objects, we do not have to visualize rays, we do not have to model rays which are coming out from within the object. All rays which are received by the surface will be reflected back. There is no rays which are generated from within the object by another light source inside. That is of course a very funny environment. More than that, when we talk of non-objects, translucent structures, then rays from other objects interreflected or from other sources will pass through that object and come out of that surface O. You have to visualize that previous figure which I shown in the slide, where the S comes from the light source, gets reflected towards V. Now you have another light source coming from the bottom of the object surface and also going towards V. I repeat again, not only S, from S direct light sources are reflected towards V, but object rays from within the non-opaque objects coming out and then also get transmitted or cast towards the viewer direction. So, opaque objects is a simplification which is easier to handle, and no interreflections approximated by ambient light. We talked about this very much, okay, that we use a constant term. Of course, that term could be dependent on V, all right, to make it realistic if necessary. If necessary, of course, do not do it always. You must know the surface you are modeling, whether it has a property such that you are looking into ambient illumination on that surface of the object, and does that ambient illumination vary with the direction of the viewer. That means, if you are viewing from this direction or from another direction, does that illumination term vary? That is what you have to model. Very difficult. So, ambient light, we talked of this hardness removed in one shot in the problem where interreflections are approximated by ambient light, and then we talked about point light sources which emanate light equal in all directions. Sun, incandescent lamps may not be large tube lights, but since that could be difficult to model, but point light sources is a very good approximation. In most scenarios, point light sources are considered, or even disc light sources, and of course, a very simplified color model. Illumination, With all these compromises and simplifications to handle and model it will consist of three parts. One is an ambient term, another is a specular term, another is a diffuse term. The ambient light, it is a case of a diffuse non-directional source of light which results from the effect of multiple reflections of light from many surfaces present in the environment. Ambient light is assumed to impinge equally on all surfaces from all directions. This also we know, and the illumination is considered to be an equation like this, where we have IA as the intensity of ambient light and is assumed to constant for all objects, and K is the ambient reflection coefficient, vary from 0 to 1, which is a property of the material. This is a K related to this rho which we talked about, the surface reflectivity, and we have a constant for the object surface in terms of ambient illumination. So, we have seen the first equation, the general model, ambient term plus direct sources F, and we have also seen an expression which can handle IA multiplied by K, which takes care of the ambient illumination and which simplifies the hardness of interreflections patterns. We will talk about the other two types of illumination models, mainly the specular and the diffuse part in the next class. We will start from here in the next class, where we will introduce the ambient light term once again, look into the equation and move into other two types of illumination models of diffuse and specular, and continue that in the next class. Thank you very much for today.